In this lesson, we are going to write code for level order traversal of a binary tree. As we had discussed in our previous lesson, in level order traversal, we visit all nodes at a particular depth or level in the tree before visiting the nodes at next deeper level. For this binary tree that I'm showing here, if I have to traverse the tree and print the data in nodes in level order, then this is how we will go. We will start at level 0 and print F, and now we are done with level 0, so we can go to level 1 and we can visit the nodes at level 1 from left to right. From F we will go to D, and from D we will go to J. Now level 1 is done, so we can go to level 2. So we will go like B, E, G and then K, and now we can go to next level A, C, I, and finally we will be done at H. This is the order in which we should visit the nodes, but the question is, how can we visit the nodes in this order in a program? Like linked list, we can't just have one pointer and keep moving it. If I'll start with a pointer at root, let's say I have a pointer named current to point to the current node that I'm visiting, then it's possible for me to go from F to D using this pointer because there is a link. So I can go left to D, but from D I cannot go to J because there is no link from D to J. The only way we can go to J is from F, and once we have moved the pointer to D, we can't even go back to F because there is no backward link from D to F. So what can we do to traverse the nodes in level order? Clearly we can't go with just one pointer. What we can do is, as we visit a node, we can keep reference or address of all its children in a queue, so we can visit them later. A node in the queue can be called discovered node, whose address is known to us but we have not visited it yet. Initially, we can start with the address of root node in the queue to mean that initially this is the only discovered node. Let's say for this example tree, address of the root node is 400, and I'll assume some random addresses for other nodes as well. I will mark a discovered node in yellow. Okay, now initially I'm enqueuing the root node, and by storing a node in the queue, I'll mean storing the address of the node in the queue. So initially we are starting with one discovered node. Now as long as the queue has some discovered node, at least one discovered node, that is as long as the queue is not empty, we can take out a node from the front, visit it, and then enqueue its children. Visiting a node for us is printing the value in that node, so I'll write F here. And now I'll enqueue the children of this root node. First I'll enqueue the left child and then the right child. I'll mark visited node in another color. Okay, now we have one visited node and two discovered node. And now once again we can take out the node at front of the queue, visit it, and enqueue its children. By using a queue, we are doing two things here. First of all, as we are moving from a node, we are not losing reference to its children because we are storing the references. And then, because queue is a first in first out structure, so a node that is discovered first, that is inserted first, will be visited first. So we will get this ordered that we are desiring. Give this some thought and it's not very difficult to see. Okay, so now we can dequeue and visit this node at address 200. And once again, before I move on from this node, I need to enqueue its children. So now at this stage we have 2 visited nodes, 3 discovered nodes, and 6 undiscovered nodes. And now we can take out the next node from front of queue. We'll visit it and enqueue its children. If we will go on like this, all the nodes will be visited in the order that we are desiring. At this stage we can dequeue node at 120, visit it, and enqueue its children. So we will go on like this until all the nodes are visited and the queue is empty. After B we will have E here. Nothing will go into the queue this time. Next we will have G here, and the address of I will go into the queue. Now K will be visited. Now at this stage we have reference to 3 nodes in the queue. Now we will visit this node at 320 with value A, and then we have C, and now we will print I, and the node with value H, the node with data H will go into the queue. Finally we will visit this node, and now we are done with all the nodes. The queue is empty. Once the queue is empty, we are done with our traversal. So this is the algorithm for level order traversal of a binary tree. As you saw in this approach, at any time we are keeping a bunch of addresses in the memory, in the queue, instead of using just one pointer to move around. So of course we are using a lot of extra memory, and I'll talk about the space complexity of this algorithm in some time. I hope you got the core logic right. Let's now write code for this algorithm. I'm going to write C++ here. This is how I'm defining node for my binary tree. I have a structure here with 3 fields, one to store data, and the data type is character this time, because in the example tree that we were showing earlier, data type was character. And we have 2 more fields that are pointers to node, one to store the address of left child and another to store the address of right child. Now what I want to do here is I want to write a function named level order that should take address of the root node as argument and print the data in the nodes in level order. Now to test this function, I'll have to write a lot of code. To create and insert nodes in a binary tree, I'll have to write some more functions. I'll skip writing all that code. You can pick the code for creation and insertion from previous lessons. All I'll write is this function level order. Now in this function here, I'll first take care of one corner case. If the tree is empty, that is if root is null, we can simply return. Else if the tree is not empty, we need to create a queue. I'm not going to write my own implementation of queue here. In C++ we can use the queue in standard template library, and to use it first we'll have to write a statement like hash include queue here, and now I can create a queue of any type. In this function I'll create a queue of pointer to node with a statement like this. Now as we had discussed earlier, initially we start with one discovered node in the queue. The only node known to us initially is the root node. With this statement queue.push root, I have inserted the address of root node in the queue, and now I'll run this while loop for which the condition is that the queue should not be empty. And what I really mean here is that while there is at least one discovered node, we should go inside the loop, and inside the loop we should take out a node from the front. This function front returns the element at front of the queue, and because the data type is pointer to node, I am collecting the return of this function in this pointer to node named current. Now I can visit this node being pointed by current, and by visiting we mean reading the data in that node. I'll simply print the data, and now we want to push the addresses of children of this node into the queue. So I'll say that if the left child is not null, insert it into the queue, and similarly if right child is not null, push it into the queue, or rather push its address into the queue. And I'll write one more statement to remove the element from front of the queue. With call to front, the element is not removed from the queue. With this call pop, we are removing the element. Okay, so this is implementation of level order traversal in C++. You can check the description of this video for a link to source code, and there you can also find all the extra code to test this function. Let's now talk about time and space complexity of level order traversal. If there are n nodes in the tree, and in this algorithm visit to a node is reading the data in that node and inserting its children in the queue, then a visit to a node will take constant time, and each node will be visited exactly once. So time taken will be proportional to the number of nodes. Or in other words, we can say that the time complexity is big O of n. For all cases, irrespective of the shape of the tree, time complexity of level order traversal will be big O of n. Now let's talk about space complexity. Space complexity, as we know, is the measure of rate of growth of extra memory used with input size. We are not using constant amount of extra memory in this algorithm. We have this queue that will grow and shrink while executing this algorithm. Assuming that the queue is dynamic, maximum amount of extra memory used will depend upon maximum number of elements in the queue at any time. We can have couple of cases. In some cases extra memory used will be lesser, and in some cases extra memory used will be greater. For a tree like this where each node has only one child, we will have maximum one element in the queue at any time. During each visit, one node will be taken out from the queue and one node will be inserted. So the amount of extra memory taken will not depend upon the number of nodes. Space complexity will be big O of 1. But for a tree like this, the amount of extra memory used will depend upon the number of nodes in the tree. This is a perfect binary tree. All the levels are full. If you can see, as the algorithm will execute at some point, for each level, all the nodes in that level will be in the queue. In a perfect binary tree, we will have n by 2 nodes at the deepest level. So maximum number of nodes in the queue is going to be at least n by 2. So basically extra memory used is proportional to n, the number of nodes. So space complexity will be big O of n for this case. I'm not going to prove it, but for average case, space complexity will be big O of n. So for both worst and average cases, we will be big O of n in terms of space complexity. And when we are saying best, average and worst cases here, it's only going by space complexity. Time complexity will be big O of n for all cases. So this is time and space complexity analysis of level order traversal. I'll stop here now. In next lesson, we will discuss depth first traversal algorithms, pre-order, in-order and post-order. This is it for this lesson. Thanks for watching.